The cloud bill spikes. Nobody knows why. Just one silent failure every turn the model asks. But the agent hands back a confused, incomplete story. It expects to see 5 tool results from the previous turn. Instead, it gets this: missing tools, missing results, confusing context, and because the context is incomplete, it tries to recover by repeating actions it believes haven't happened yet, again, and again, and again. The result? A corrupted feedback loop and a cloud bill that keeps climbing. I'm going to show you exactly how this happens, why standard debugging will lie to you, and the fix. 5 tool calls ran. The agent's own step counter says 2. Tool results all claiming to be step 0. 2 steps just vanished. No exception, no stack trace. No 500. It ran, it answered the question, and it quietly lied about what it did. That's the failure mode nobody's alert is built for. Here's what success looks like. 5 steps. 5 results. In order. Step 0 gets weather. Step 1 gets calendar. Step 2 sends email. Step 3 gets more weather. Step 4 gets more calendar. The counter matches the history length. 5 and 5. Everything is clean. What we are building. This is the state manager for the agent loop, a function called record result. Let's walk through it line by line. This is the key to understanding everything that breaks. When a tool finishes executing, it calls this method. The tool name might be getWeather. The result might be 89 degrees, clear. The first thing it does is read the current length of the history array. This is how it determines what index to assign to the new entry. If the array has 3 entries already, the length is 3. So the new entry gets index 3. The next slot. Next, it appends a dictionary to the array. The dictionary contains the step index, the tool name, and the result. Finally, it increments the completed steps counter by 1. This keeps a running total of how many tools have been executed. In the sequential version of this agent, this function is called one at a time. Tool 1 finishes. Record result runs. Tool 2 finishes. Record result runs. Tool 3, Tool 4, Tool 5. Each call has the complete up-to-date state. When Tool 1 finishes, the history length is 0. It gets index 0. History length becomes 1. Counter becomes 1. Tool 2 reads length 1, gets index 1. Appends. Counter becomes 2. This is correct. It's boring. It's reliable. It's also slow. 0.7 seconds. In production at scale, that latency adds up. Here's where the trouble starts. A developer looks at this sequential loop and thinks, these tools are independent. Weather doesn't depend on calendar. Calendar doesn't depend on email. They don't need to run one after the other. So they wrap the loop in a ThreadPoolExecutor. This is the entire diff. The for loop becomes a thread pool. It passes code review. Every tool call in the batch genuinely is independent, so parallelizing the tool calls themselves is fine. Nobody re-audits record result, because record result didn't change. The diff passes code review. The reviewer checks the data dependencies. None exist. They approve it. This is the psychology of the code review. The dependencies are independent, so the threading is safe. But the reviewer missed one thing. The tools themselves are independent. The state manager is not. The record_result function touches shared state. History array. Step counter, both read and written by multiple threads. In the first turn, there were 3 tools. All 3 raced. All 3 raced, index 0. All 3 overrode each other. Only the last one survived. The other 2 vanished. This is what happened. 3 tools into 1 slot. The next 2 slots, empty. You want to fix it. The natural instinct, add print statements, see what's happening. You add print statements, you rerun the code, and look at this. All 5 results appear. No collisions. Everything seems fine. You think the bug must have been somewhere else. The threading looks fine. You ship it. But here's the trap. Printing to standard out is slow. It takes time, milliseconds. When you add a print statement inside the critical section, you introduce delays. The print statement changes the timing. The threads no longer arrive at the same time. The race condition disappears. This is what we call a Heisenberg bug, a bug that disappears when you try to observe it. The act of debugging changes the behavior you're trying to debug. You add try except blocks. You catch exceptions. You log errors, but there are no exceptions. The append succeeds. The increment succeeds. Every line executes without error. The state is just wrong. Here's where I'd stop most engineers and ask, which of your alerts catches this? If you're using the 4 I've talked about before. Semantic success rate. Per tool call success rate. Cost per successful request. Steps to completion. Semantic success rate. The agent still answered the question. Passes. Tool call success rate. Per tool. Every individual tool call succeeded. None errored. Passes. Cost per successful request. 5 tool calls still happened. Tokens still got spent. Request still counted as successful. Passes. Steps to completion. This is the one that moves, but it moves the wrong direction. It goes down. A shorter loop reads as healthy, not broken. That's the trap. Your best leading indicator for the agent is confused. Is the one metric a silent race condition can quietly improve? None of your 4 numbers tell you to look here. What gets you here is a trace. Here's where observability tools earn their keep. OpenTelemetry spans with custom events. There are 4 span events. 4 moments capture. Event 1, history index read. Captures the index. The thread reads. Event 2, history append. Captures the index the thread actually wrote. Same value it read, nothing rereads it in between. The collision isn't one thread's read disagreeing with its own write. It's 2 different threads reading the same index before either one has written. Event 3, step counter read, captures the value the thread reads. Event 4, step counter write, captures what it wrote. Always exactly 1 more than it read. Same pattern. When 2 threads both read the same starting value, 1 increment gets lost. Together, these 4 events tell the complete story. They turn an invisible race condition into visible data. That's the power of observability. Nothing about the bug changes. We're just finally able to see it. Watch the timestamps, not the thread names. 3 threads, 3 tool calls, and every one of them reads index 0. None of them had written yet when the next one read. That's the entire bug, timestamped. 3 reads, 0.151, 0.161, 0.151. 10 milliseconds separate the first and the last. The first write doesn't land until 0.171. The write is what updates the number. Nothing else does, but the write is slow. 20 milliseconds slow in this build. So for 11 of those milliseconds, 3 threads see the same stale number. None of them know the other 2 exist. Each one just trusts what it read. Trust the read, skip the check. That's the whole bug right there. Turn 2. 2 tools this time. Weather and calendar. IDX read equals 3. Both threads. That's the history race again. The value read equals 1 in both threads. That's the counter race again. From turn 1 already having cost 1 increment, 3 threads should have pushed it to 3, but only reached 1. Turn 2's race doesn't just add a second lost increment, it's racing off a counter that was already broken by turn 1. Same 11 millisecond window causing both at the same time. Turn 2 doesn't just add a second race, it races on top of the first one's damage. Same mistake, twice, and this time it's compounding, not just repeating. So the final diagnosis is classic talk 2. Time of check to time of use. You check a value, then use it later, and by then it's already changed. And this bug exists all over the industry. Anywhere shared state gets updated from parallel execution without synchronization. Here's what makes this genuinely hard to catch. It's not non-deterministic in the way you expect a race to be. This isn't random. It's rigged. Deliberately, so it happens every take. But in your actual production agent, the timing depends on real network latency to real tools. So the corruption pattern shifts between requests. Some runs look fine. Most look a little off. None of them crash. And every symptom points at the wrong layer. Steps not incrementing right looks like a prompt issue. History looking corrupted looks like a serialization bug in your framework. Nobi's first instinct is check whether 2 threads wrote to the same list index at the same time. Because nothing about the stack trace, because there isn't one, tells you threading is even involved. Here's the fix. 1 lock, around exactly 4 lines, not around the tool execution. Only around the state bookkeeping. The lock creates an atomic transaction. It ensures that only one thread can execute this block at a time. When thread A enters, it acquires the lock. Thread B waits. Thread C waits. Thread A reads the length. It's 0. Appends at index 0. Counter becomes 1, then releases the lock. Thread B now sees the updated length. It's 1, so it gets index 1, no collision. The tool execution still runs in parallel, 3 tools executing at the same time. But when they finish, they line up at the lock. Only one writes to the state at a time. Now look at this. All 5 steps, all 5 indices, all 5 results. The counter says 5. The history length is 5, no empty slots, no collisions. And the wall time? 0.32 seconds. Faster than the broken version. The lock only serializes 4 lines. The tools still run in parallel. It's faster and correct. And look at this. The invariant check. After every write, it verifies that the counter matches the history length. If they ever disagree, it raises a runtime error. It fails closed. It fails loud. You get a stack trace in your logs, not a silent corruption in your production database. Here's the senior engineer's rule. Don't synchronize the whole function. Only synchronize the critical section. Identify the exact lines that touch shared state. Read, modify, write. Those need atomicity. The tool execution stays parallel. The bookkeeping stays serial. Here's your rule for tomorrow's pull request. Identify all shared state. Find every read, modify, write sequence. Wrap those critical sections in a lock. Verify the invariant after every write, and fail closed, not silent. Don't let silent state corruption ruin your production system. Instrument your code. See the race. All the code is in the GitHub repo linked below. If you have questions, drop them in the comments. If this helped you, subscribe.